Hi friends, I'm Divyansh Ameta and I'm with my friend Jayesh Bankoti, and we are going to discuss on the topic some basic fundamentals of aerodynamics of a projectile. In this discussion, we are going to cover basic ideal projectile motion, its equation, and how these equations change in real life scenario with air resistance and other factors. We'll also see the design aspects which are under consideration for shape selection of a projectile.
So next we are going to compare ballistic flight versus the actual flight. In a ballistic flight, the flight of the projectile, it is a flight of a projectile which assumes that the weight is the only force acting on the projectile. Hence, in the influence of the gravity, which is the only force acting on it, the trajectory is a perfect parabola. In reality, the projectile in flight generates a moderate amount of aerodynamic drag. Hence, it's not strictly ballistic, and the shape of the trajectory is not a parabola.
Now let's have a look at some important terms. Terminal velocity. Terminal velocity is the constant speed that a freely falling object eventually reaches when the resistance of the medium through which it is falling prevents further acceleration. Or in other words, when the projectile is in its highest position, it starts free falling, then it reaches a point where its weight is equal to the air drag that the body is experiencing, and after that point the projectile experiences no force. The velocity of the projectile at that point of time is called terminal velocity. As here we can see, by equating weight and drag, we obtain the terminal velocity, which is equal to under root 2 mg upon CD rho into A, where CD is the drag coefficient and rho is density of air.
So now let's look at the important derivations for the equations of motion for a projectile in real life, that is with air resistance. So let's consider at the launch the projectile is inclined at some angle to the vertical. So we will resolve the initial velocity into vertical and a horizontal component. Unlike the ballistic flight equations, the horizontal component includes the action of aerodynamic drag on the projectile. We'll first consider the vertical component and then develop the equations for the horizontal component. So we'll divide the trajectory into two parts: vertical descent and the vertical ascent. So in vertical ascent, the force acting on the projectile will be in downward directions. The gravity and the drag will be acting in the same direction together. So the total acceleration hence can be found by equating it to ma. As we have found out the acceleration, we can hence find the velocity with the use of integration. And for the topmost point, we can know that at the topmost point the vertical velocity will be 0. Hence the Ymax can be found that way. For a horizontal motion, the force totally will only be a drag force acting in just the opposite direction. So for the horizontal force, there will be an acceleration which will be dependent on the velocity square. Now acceleration is v dv by dx. So using this and with the integration, we can find out velocity as a function of x. Hence, and further way, we can find out the distance traveled with time. Now for the vertical descent. Now here's the term where the terminal velocity kicks in. So the vertical descent, the gravity and the drag force will be acting in the opposite direction. So, in the last slide, we talked about the motion for a point mass. So now let's take this to a rigid body dynamics. So in a rigid body, three motions due to air drag will be yaw, pitch and roll motion. So these three motions are actually important because the reduction of these motions will help in a stable flight and trajectory. How that will happen? So now let's see. If the yaw motion is present, hence the vertical axis will be moved out. Due to this, the actual path will not be followed by the projectile. If the pitch rotates, then the lateral axis will be changed and hence the range will be affected. And with the roll motion, as you all know, with the rotation of the projectile, there will be a Magnus effect happening, hence the projectile will deviate from its path.
Considerations for shape selection. We select the shape of a projectile so as to achieve the following. First, to achieve a aerodynamically stable flight, and second, to achieve the desired range. For achieving the aerodynamically stable flight, the center of gravity and center of pressure need to be at a distance, and the center of pressure should be towards the tail of the projectile, while the center of gravity should be towards the head part. And for the desired range, projectile should neither fall near or far from the target, so its trajectory should not deviate in transverse direction. That is, we have to minimize yaw, pitch and roll motion. So that's the end of our presentation. Thank you. For more such interesting videos, subscribe this channel, like and share.